Hi, today we're going to talk about gas mixtures and partial pressures. Okay, and Dalton's law of partial pressure is that the total pressure of a mixture of gases is equal to the sum of the pressures of each gas as if it were present alone. So it's the sum of the partial pressures. Okay, so if I have three components in this gas mixture, then basically it would be the sum of the three partial pressures of each gas. When we look at this, so let's take a look at PA. So if I look at gas A, then that's going to be equal to the number of moles of that gas A times RT divided by V. Now keep in mind, if I have a vessel that has gases A, B, and C in here, then the volume for all my gases is the same, and the temperature needs to be the same. It's not like you're going to have a different temperature for gas A than gas E. It's like being in the room and having one corner of the room be super hot and the other part of the room being super cold, and then averaging out a third of the way in the room. So all of the temperatures have to be the same, all the volumes have to be the same. So the only thing responsible in this case then for the partial pressure of A is going to be the number of moles of A in a mixture of gases. If we do that, then let's go ahead and plug that in. So the pressure, the total pressure of T is equal to the moles of A, RT over V, plus the moles of B, RT over V, plus the moles of C, RT over V, etc. Okay? So, this is equal to the total number of moles, okay, times RT over V. Okay, so just so you know, so the total moles of gas is equal to the moles, the sum of the moles of gas. But what's more interesting is this. If we look at my partial pressure of A, okay, let's go back to here. The partial pressure of A relative to the total pressure is going to be equal to NA RT over V divided by N total RT over V. Okay, if we rework this equation, the RT's cancel out, V's cancel out. It turns out that the partial pressure of A is going to be equal to the moles of A over the total moles of gas times the total pressure. This is called mole fraction. Okay, and we use a capital chi to represent mole fraction. So PA is equal to the mole fraction of A times PT. All right, so let's do an example. Okay, so at 1 atmosphere, or let's say at sea level, my total pressure, let's say, is equal to 1.018 atmospheres. We know that the mole fraction percentage, the mole percentage of nitrogen in air is equal to about 78%. Okay? If we do that, so then what is the partial pressure of nitrogen in air at sea level. Oh, can't spell level today. At sea level. So in order to solve this, we basically know that the partial pressure of nitrogen is equal to basically my mole fraction of nitrogen in air times the total pressure. So we know 0.780, because I converted that to my fraction, times 1.018 atmospheres. So the partial pressure of nitrogen is equal to 0.780 times 1.018 is equal to 0.794 atmospheres. Okay, so that's how we use partial pressure. We also can use partial pressure for two other systems. So let's just discuss the first system, and that is a partial pressure of oxygen. Okay, so the partial pressure of oxygen, say at 1 atmosphere, okay, this pressure, we know that oxygen is about 23%, okay, or 22.9. We'll give you 22.9. Okay, if we do that, then the partial pressure of oxygen is going to be equal to 0.23 atmospheres. So this is basically, if we live at sea level, what our lungs and our body is accustomed to. However, if we say we're going diving, and for every, I believe it's 30 feet you can go down safely. I think it's for every 3 meters it increases in atmosphere. I'll double check on that value. But suppose someone goes down 9 meters, okay, 2. So that would be like 3 atmospheres. Okay? What is the partial pressure of oxygen? What we find is the partial pressure of oxygen is going to be equal to 0.229 times 3 atmospheres. Okay, that's 0.6869 atmospheres. Okay. So why is this of any interest? Well, if you happen to be exposed to high pressure systems, like if you tend to go scuba diving or tend to go into a pressure chamber to repair some system, the bottom line is that when we talk about the pressures, this means that when you're breathing in air, your partial pressure is 0.69 atmospheres. This is 3 times what our bodies, our lungs are used to. And there's a very narrow range in terms of what our lungs can take in terms of the partial pressure of oxygen. Likewise, when we talk about nitrogen, for nitrogen, because of the increase in pressure, there's an increase in partial pressure here as well. What that means is that the nitrogen gas tends to dissolve in your bloodstream at higher pressures. And that's what we hear when we talk about the bends. When a diver actually goes under high pressure, the nitrogen dissolves, because of the increase in partial pressure, dissolves in the bloodstream. But as you surface and the pressure decreases, now your bloodstream has too much nitrogen and the nitrogen gas has to bubble out. When it does that, if you're not breathing enough of it out, it'll bubble out in your body. And that's what we call the bends, because you're forming little pockets of gas in which you can have clots. So that's why knowing this. And in fact, what deep sea divers do is they don't use air when they know they're going to be going under extreme pressures. They use a heliox mix, which is helium and oxygen. And by knowing how deep they're going to dive, they can determine what's the appropriate ratio of helium and oxygen to make sure that they stay in the biologically relevant partial pressures of oxygen and not to have it increase so much that they develop actually the bends. Actually, in this case, you wouldn't because of helium, but have difficulty with excess oxygen that they're breathing.